So last non-programming lecture, we were talking about logic. We learned some cool truth tables, some cool operations, and or not, and some fancy ones. And then we started talking about binary. Binary is a new number system where you only have ones and zeros to work with. We think in decimal, base 10, we have 10 digits to work with, but in binary, it's base 2. You only have 2 digits to work with. And remember that a bit is a binary digit, and a byte is 8 bits long. It's like a unit of space inside of a computer. So let me show you how to convert from binary to decimal. Like if I give you a bunch of ones and zeros and I say it's a binary number, how can you figure out which one it's meant to be, which real number that you understand in decimal? So I will use the subscript, right? I'll say base 2 if I'm talking about a binary number, and I'll say base 10, subscript 10 for a decimal number, okay? And actually, the way that you can break this down and convert it back to decimal is very similar to the way that you learn to break down decimal numbers in like elementary school. Do you remember when you were forced to do this in elementary school? You're like, all right, 1,234, that is equal to 1,000 plus 200 plus 30 plus 4, yeah? And then once you started learning about exponents, you figured out like, oh, that's 1 times 10 to the third plus 2 times 10 squared plus 3 times 10 to the first plus 4 times 10 to the 0, yeah? So notice where the base appears. This idea generalizes. You give me a binary number, you do the same thing. You just do times multiples of the base, which is now 2. Okay, does that make sense? So let's do that. So that means, right, 10010 in binary. What is that? Let's convert it to decimal. Well, this is the 2 to the zeros place. This is the 2 to the ones place. This is the 2 squareds place. Let's convert it. So it's going to be, start with the rightmost digit. That's 0 times 2 to the zeros place. Always starts at the zeros place, like 10 to the zeros place, 2 to the zeros place. And then it's plus 1 times 2 to the ones place, plus 0 times 2 to the squareds place, 2 to the twos place, plus, oh sorry, that was a 0. Honestly, you don't need to count the zeros, but it's helpful to see it the first time. And then this is 0 times 2 to the third, right? 2 to the thirds place, the eighths place. And then this is 1 times 2 to the 4. So that's like the 16ths place. Interesting to think about. So that's the operation. Notice where the base appears. It's the digits times power of those base times power of the base, and you're working your way from right to left. So you simplify this. This becomes what? All the ones. Excuse me. There's 1 times 2 to the 4 plus 1 times 2 to the first, which is 16 plus 2. So this number 10010 in binary is really secretly the number 18 in decimal. Okay? You just do that kind of power expansion and it all works out. Are there any questions about what I just did? Do you think you could do it? That's how it works. That's the process. So here, let me show you this. Here's the rule. Here's the process. Now you try. You can go to let's go to the written ice page, why not? Make sure to do your attendance. I'll stop that after we finish this question. But please go to the written ice page. You guys can work together if you like, but help each other. And let's see what we're thinking. So here is 1111 in binary. I'd like you to convert that to decimal, please. Okay, so you understand the assignment. This is the biggest 4-bit number, right? It's got 4 ones. So that's the biggest 4-bit number. What is it in decimal? See if you can use this process and figure it out and write down your answer. Okay? Give that a try. Remember, the rightmost one is the 2 to the zeros place, not the 2 to the ones place. What you're thinking. If you're agree, you only need to spin once. And help each other. So you're going to get very good at powers of 2 in this class. And if I convince you to become a computer science major, an engineering major, it'll be good for you. It's worth remembering. Alright, I feel like our voices are dying down. I'll give you a few more seconds to type in your answer if you want to. Let's see if we agree. Alright, so okay. A couple of us thought 15, one of us thought 14. Let's see what the true answer is. Let's figure this out together. Alright, so still, this is the pattern. And this is the pattern. Thank you for your help, for your thoughts. Oh, another 15. Oh, 13 now instead of 14. Okay. I'll stop that. Let's do it together. So, alright, the biggest 4-bit number. We got, this is a 1, right? 1 times 2 to the 0. Plus another 1 times 2 to the 1. Plus 1 times 2 squared. Plus 1 times 2 cubed. And so that's going to be 2, 4, 8, plus 4, plus 2, plus 1, this is what, 10, plus 5 is 15. So the answer is, in fact, 15 in decimal land. Any questions about that? So the biggest 4-bit number is the number 15. That's what it's really saying. So that's the process. That's how it works. Do yell at me if you have any questions about that. But I'm here to tell you that that's the easy way. I give you a number in binary. It's very easy to do this process to calculate its decimal equivalent. It's much harder to go the other way. So I need to teach you the other way now, and it will take some more thought. All right, so let's go. Let's say I give you a decimal number, and I have you convert it to binary. That's the backwards process. Okay, this is more difficult. It requires you to repeatedly take remainders as well as divide. All right, it's going to look a little ugly. It's a little unfortunate. But you remember how to take remainders, right? If you learned about this, like the first way you learned how to divide, right? You like the teacher said, divide 123 by 10. Dun dun dun. What do you get? It's 12 remainder 3, right? And so I'm gonna be using this operation that gives you the 12, and then also the operation that gives you the remainder. And that's so important. I'm gonna have a whole symbol for it. It's called the modulus symbol. So if I put a percent sign in between two numbers, I mean divide them and give back the remainder. Right? So don't give me the 12 back, but give me the 3. All right? And this operator, it exists in many programming languages. It's called the modulus operator. So I'll say mod for short. I'll say calculate please 123 mod 10. That's do the division and then give back the remainder rather than the quotient. Okay? So that's the idea. So the key here is it's going to generalize back to this idea again. So like normal decimal stuff. I'm going to show you something in decimal, and it's going to generalize to binary all over again. All right. So the key thing that we want here is we'd like to extract the digits from a number, be it in decimal or binary. All right. So here's the secret. What is the algorithm to extract all the digits from the decimal number 123? Let's say like I have this number, but I can't look at it. It's in like a variable somewhere. I don't know what's there, but I want to extract all the digits. I want to like pick out the 1, pick out the 2, pick out the 3. I want to get the individual digits of a number using math. How do I do it? Well, here's the secret. Here's the algorithm. You can always get the rightmost digit of any number. You can always get the rightmost digit, for example, the 3 here, by dividing by 10. Yeah? Because that remainder that you get when you divide by 10 gives you the rightmost digit, the 3, yeah? You see that? So now you know how to always get the rightmost digit of any number. So if only I can convert, if only I could get from 123 to 12, then I can get the rightmost digit of that, get the 2 out. And then shift away the 2 as well, make it smaller. So how do you convert it? How do you chop off the last digit of a number? Well, you do the other piece, right? You do the division, and you look at the quotient, the thing without the remainder, yeah? Don't deal with any decimals or anything. Divide by 10, throw away the remainder. Does that make sense? It's called integer division in programming languages, but it's just like the grade school division where you just chop off the remainder, say that the answer is 12. Okay, so that's how you can convert from that number and chop off its digit. And now you know, once you're working with 12, you can do the same thing. Mod 10 again will give you the 2, because it goes in once with 2 left over, right? That's the remainder when you divide by 10. And then you can just keep playing that game all day long until you hit 0, you're done with the process. So here it is. Here's how you extract the decimal digits of the number 123. You start by doing the modulus. You do mod 10. And that will give you the rightmost digit, right? That will extract the 3. Yeah? And then I'd like to get the rightmost digit of the smaller number without the 3. So let's shift away the 3. Let's chop it off by doing division and throwing away the remainder. So it's like 12 with 3 left over, 12.3. Throw away the 0.3. Throw away that remainder. Just give me the 12. Okay, that's a different kind of division than you're used to these days. But that's the secret. Because now this algorithm can repeat. Now I can work with the 12, extract its rightmost digit. 12 mod 10. That will give me the rightmost digit there. That will give me the 2, because right by 10 it goes in once with 2 left over. 2 is the remainder. And then I want to like extract the 2, shift away the 2, convert it to just 1. So I'll do 12 divided by 10, throw away the remainder. The answer is 1. See that? It's 1.2, so you throw away the 0.2. And then, all right, let's extract the rightmost digit of 1. This algorithm is kind of dumb, but this is how you know when it stops. Extract the rightmost digit of 1. 1 divided by 10 goes in 0 times with 1 left over, so there's my 1. And let's shift away the 1. Let's shift it away to the right into the ether by dividing by 10 and throwing away the remainder. It goes in 0 times, right? 0 times with the 1 left over. So the 0. Once you hit 0, you're done, all right? And every time you took a modulus, every time you took a remainder, you got a digit of that number in reverse order. So if you didn't know what it was, now you do. That's how you can extract every digit of a number. Does that make sense? Any questions about that? So look at where, look at where the base appears. I'm extracting the decimal digits of this decimal number because I'm doing mod 10 divide by 10. If I change these 10s to 2s, I'll start extracting binary digits, bits, and shifting away those bits and getting the next rightmost bit I should find. That's the secret. So this generalizes all over again. It's just a more complicated process, right? So here's how you do it. You repeatedly extract the rightmost digit in binary by mod 2 rather than mod 10, okay? And then you shift away that thing, that bit that you just discovered, by divide by 2 rather than divide by 10. So this generalizes to binary. It's all going to work out. So here's the answer. Okay, so let's do 8, the decimal number 8. Let's convert it to binary by doing this process using mod 2 and integer division by 2. So the very first thing I want to do is 8 mod 2. I want the rightmost bit of this number, binary, okay? 8 mod 2, well, it goes in 4 times with nothing left over. It's an even number, so there's nothing left over when I divide by 2. Okay, so 0, that's the rightmost digit. The rightmost digit of 8 in binary must be 0, okay? And now I want to shift away that 0 from the 8, like chop off that bit of 8, which is weird to think about, but it works. So I'm going to do 8 divided by 2 to get rid of that rightmost 0 and find a smaller number to convert to binary, all right? Throw away any remainder. There is none this time. So 4. If I just convert 4 to binary and slap a 0 on the end, I've got my answer. Okay, that's how this works. So now I'll do 4 mod 2. Let's get the rightmost digit of 4 in binary. Well, it goes in 2 times with 0 left over, right? And let's shift away that 0 that I just discovered. That's the next second to rightmost bit, right? 4 divided by 2, throwing away remainders. There are no remainders, but so the answer is 2. And then again, let's get the rightmost digit of 2, rightmost bit of 2 in binary. 2 mod 2. Goes in once with 0 left over. Let's shift away that 0 to divide by 2, throw away remainder, get a 1. Let's convert 1 to binary. 1 mod 2. Sorry, this is getting a little small. 1 mod 2. Goes in 0 times with 1 left over. Shift away the 1. 1 divide by 2, throw away the remainder. Answer is 0, we're done. And now every time I took a modulus, every time I took a remainder, I got an answer. I got a digit. I got it in reverse order. Oops, that was supposed to be green. I got it in reverse order. Alright, so the answer is 8 in decimal is equal to 1000 in binary. And that's your answer. And you can check that, right? This is 2 to the 0, 2 to the 1, 2 squared, 2 to the 3's place. That is 8. works out. You can always check your answer very easily, but the process is a little tough. Okay? Any questions about that? So that's going to work if you follow that algorithm. All right. So here, you try this one. Let me clear out our answers from before. So like refresh the page. Don't fill in your old answer because that won't work. Refresh the written nice page. Now they're empty again. And you try it this way. Here's the process. Here's the number 25 in decimal. Try to convert that to binary now. All right, using this idea. So I'll give you a few minutes to think about that. That's going to take some math. And I'll do it with you. The rightmost digit binary of 25. So it's going to be 25 mod 2. You're going to have to calculate that. So divide 25 by 2. What is the remainder? There is a trick for 2. Like that we all have our calculators out. If you finish early, you know how to go the other way, right? So check your answer. Alright, that's my idea. That's my timer. Let's see your ideas. Ew, we disagree. Those of us who have pressed submit so far. Okay, got a majority going on there. Nice, nice, nice. Any other thoughts? We are a little bit all over the place, but that's good. This is why we're asking this question. So, I was looking something up. Let me click this really quick. It's not even there. So let's see. Let's see what the answer is. A few of us think 11001. That's like the one I see the most of. But let's see what we're thinking. So yeah, thank you for that. I'll go back. And remember that you're getting digits in reverse order. That's also important. So let's do it. Let's do it together. 25 We want the rightmost bit of that in binary, so 25 mod 2. A quick way to notice like what the answer is after doing a remainder, it's going to be like, if it's odd, it doesn't go in cleanly to 2, right? And so there's going to be 1 left over. There's going to be a 0.5, so it's going to be remainder 1 when it's odd. So 1 is the rightmost digit of 25 in binary, rightmost bit. Then I want to get rid of that 1 by dividing by 2. So it's, 12? Yeah, 12.5, so 12. Throw away all of the remainders, okay? Can't speak today. So now if I just convert 12 to binary, I'll have the answer. So I'm going to do 12 mod 2. It's even, so 0. 12 divide by 2, throwing away the remainder, though there is none. We get 6, and so now I have a smaller number. Again, convert 6 to binary, slap a 0 and a 1 at the end of that, we're good. Okay, that's the goal. So now do 6 mod 2. Even, so 0. Shift away that 0 by doing division by 2 and throwing away any remainder if there is one, making 3. So now I'll convert 3 to binary. I'll get its rightmost bit. 3 mod 2. That's 1 because it's odd. Shift away that 1 by dividing by 2. The answer is also 1, surprisingly, because it's 1.5, right? Throw away the remainder. And then let's convert 1 to binary. You kind of know the answer by now, but we'll stop when we get 0. So 1 mod 2 goes in 0 times with 1 left over. Shift away the 1 by dividing by 2, we hit 0, and that's how we know we're done. Okay, so every time we took a remainder, did the modulus by 2, we got a digit in reverse order. And so, yeah, I think a lot of us had it. It was 11001. Do you see that? So it's in reverse order, remember. That's important. That is a bit confusing. So that's the answer. Base 2 if you want to be specific about it. And you can always check this. This is the 2 the 0's place or the 1's place. This would be the 2's place, the 4's place, the 8's place, the 16's place. So just to quickly check, it's 16 plus 8 plus 1. Is that 25? Yeah, 16 plus 9, 25. That's how you can tell. That is what you wanted. Any questions about that process? It's a bit complicated, but that's how you can always make it work, going from decimal to binary. Okay. Okay. Now that we're comfortable with binary, let me show you something weird. Let's add binary numbers. It's going to look so odd to you. So first of all, what are these two numbers? This is, we know this one, we converted it. This is 15, right? And then this one is 15 minus 2, because this would be the 2's place, so this is 13. And this is not base 2, excuse me. This is the base 10 version of the number. So really, this is we're trying to add 13 and 15 together. And you know how to add stuff. It's like 8, 2... It's supposed to be 28 for the answer, but how do you get that in binary land? How do you do binary math? Watch. So, alright, just do it rightmost digit as you normally do, but you got to do it in binary. So what's 1 plus 1 in binary? Well, the answer is 2 in decimal. But what's 2 in binary? You got to carry already, right? It's a 1, 0. See that? Very good. So now I have to add all these 3 bits together for this place. So it's 1 plus 1 again. Again, it's 2. In binary, that's 1, 0. So I'm carrying a 1 already. 1, 1. Or sorry, 1, 0. Excuse me. And now I have 1 plus 1 plus 1. And you compute the number 3. And so, what is 3 in binary? It's 1, 1, so I got to carry a 1 again. So 1, 1. And then again, 3 ones together is the number 3, but in binary that's 1, 1. Okay? So that's how you can compute that. You can do math in binary, just got to carry a lot sooner than you normally would. Does that make sense? A little weird. But, yeah, it works in any base, so you just got to remember to carry once you hit the end of your digits. Okay? So you might be wondering, well, first of all, I guess you know already that stuff is stored in a computer in binary format. That's important. That's cool. But then also computers work using binary, right? They're gonna pass along information using 1s and 0s as well. So let me kind of tie it all together by showing you a circuit that adds numbers, because we learned about circuits too. All right? So like, I'll try and answer this question in the last slide. Like, how does your computer actually use these 1s and 0s in binary to do meaningful work? Every number, if you have a calculator app on your computer or your phone, it's got the numbers in binary. And then it's doing this kind of addition on them and showing you the answer back in decimal real quick. Okay? So it's really doing addition, and it's doing it like this. There is a circuit for that. Do you see that the exclusive OR operation, works a whole lot like addition. You remember that one? That's this one up here. If true is a 1 and false is a 0, you see how 1 plus 1, that's 1, 0. The rightmost bit is 0. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. Exclusive OR is doing addition on a single bit. Forgetting about the carry, though. We can deal with that separately. But, yeah, exclusive OR is essentially the same as 1-bit addition, because 1 plus 1 is 1, 0. The rightmost digit is 0. So it's doing it right, okay? So if you just plug your 2 bits into an exclusive OR gate, you get out the sum. And then if you need to remember what to carry, like if it was 2 1s, right, you need to carry a 1. So you can just, like, how do you get a 1 if they're both a 1? You shove it into an AND gate. The AND operation will compute a 1 if they're both a 1. That can be your carry bit. See that? And then so you just chain a bunch of these adders, adding circuits together. Eventually you're going to need a carry in as well as a carry out, so this is the full idea. It looks a bit more complicated, but it's a bunch of exclusive ORs to do bit addition, and then like you have a carry coming in and a carry going out, okay? And you just chain. You chain all of these a bunch of times, as many times as you need. I want a 32-bit number to store big stuff. And that's how you do addition inside of a computer. It's just sending 1s and 0s through the circuit really fast, chaining it properly. Isn't that fun? So you can build a computer with this stuff. It is worth understanding and worth knowing. Okay. Any last questions about any of that before I switch topics? So we're like in a weird in-between state. All right, that's pretty cool. I think it's worth understanding. I'm very biased though. So let's change topics to still computer sciencey things. Let's talk about privacy and encryption. So fun things that involve fancy numbers, right, inside of a computer. So let's talk about privacy because we operate on the internet, right? We have things that are connected to many other things. Do we have privacy in the digital era in which we live? Let's figure that out, right? So we got, at least in the U.S., we have the Constitution, which has the 4th Amendment on it, which prohibits unreasonable searches and seizures. That's kind of important. That's kind of implying some stuff, right? I have no idea why okay, pens work fine now. Weird. Okay, so yeah, if you want to search somebody's house, you need a warrant, you need probable cause, all that fun stuff. So that's kind of nice. That means nobody's just going to walk into your house one day without reason. But the internet is not your house, right? It's different. It's like you're connected to the government right now if your phone really wants to go to one of those websites, isn't it? It's very different from just like having your own property. So this is a little bit of a gray area. And back in the day, actually, the Supreme Court, like when phones first started coming out, because like they were connected along the phone lines to places that weren't only your house, the Supreme Court ruled back in the day that you did not need a warrant to tap a phone and listen in on somebody's conversation if you were law enforcement, because they considered a conversation to not be a tangible object, something that you can touch. So it's like, that's fair game. You just listen in on that if you want to. So luckily, they changed the way that they thought back in the 60s. But it really is all about the law at this point. Like what laws are given to us. How do people interpret it? So yeah. Still a bit of a gray area. Do we have privacy on the internet? So let's talk about a few examples. So I have just a bunch of examples to tell you about today. Some anecdotes, fun stuff. So this is from about a decade ago now, I would say. Target, the company, did some data mining on the people that shopped at Target. And the word data mining, if you haven't heard it before, is just like when you make a purchase at Target, they know what you bought. They know your credit card number, even if they don't know your name. And then they have like the history of like what you've been doing, what you've been purchasing. So it's just essentially data mining is just taking a bunch of data and looking for patterns. It's a glorified way of saying pattern matching. Usually with the goal of making money. So Target noticed that pregnant women would buy certain products at certain stages of their pregnancy, right? Because you need different things at different times. And Target discovered that through their data mining. And they took that information and they started sending targeted coupons and ads to the women. And I love that word exists. It's a great pun right there. So that's crazy, right? They took all this data and they used against it to try to make money. So the question that I have for you is, does this infringe on the privacy of the shoppers at Target? What do we think? Right? It's an open-ended question. There is no right answer. Should they be allowed to do this kind of data mining on what you bought and save that information for later? Right? So again, you can ask your boys if you're not sure what to think yourself just yet. You can ask Kant, like he'd ask a question with the word always in it. He'd be like, should everyone always be looking at somebody else's purchase history and trying to find patterns in an effort to make money? Kant is big on individual rights, so he'd probably say no. It's like using a person as a means to your end, right, of making more money. So I would say Kant would probably say no to it, but utilitarians would say, is there any utility in this? So you can argue both ways. You can be like, no, it infringes on the women's privacy or just any shopper's privacy. I'm sure they do more now than just like targeting pregnant women. But you could say that that's a big hit on privacy and that's not okay and that outweighs any other benefit. On the flip side, as a utilitarian, you could be like, oh, well, the pregnant women would be buying these products anyway, and so they're saving money but with these coupons, right, if they use them. So that seems like a win-win. And so you can argue also that, yeah, it's a good thing. But again, it's up to you. It's a little crazy, right, that a company can just look at your history and start sending you ads for things that you've bought. I'm sure you've seen this, right? You search for something on Google, and then you go on Amazon, and like that's the first sponsored thing or something. Disgusting. But is it a good thing or a bad thing? That's up to you. Okay? I have my own thoughts. So that's one anecdote. We can also talk about ad blockers. I am very much a proponent of ad blockers. I don't like ads. So I highly encourage you to download this extension called uBlock. It's wonderful. But this was a hot topic, all right? So ad blockers, if you install one in your browser, that is technically illegal. It's not illegal to block ads, but certain things are illegal. You know, like you go to certain websites like the New York Times, and it's like you've viewed, or even the Fresno Bee, it's like you viewed your 3 free articles this month. You can't read anything else now, unless like you clean your cookies out or something. So it's not illegal to block ads, but it's technically illegal to block ad blocker detectors, which is a weird, funny gray area. So you've maybe also seen websites that pop up like, turn off your ad blocker if you want to use this website. The ad blockers themselves are not allowed to block that message, even if you have one installed. All right. So that's a little weird, but cool. And the reason behind that, at least in the US, is like you're tampering with a website's access control. The second you do that, the second you block their detection factors. And as a website, you have a right to control access to your content. Usually, like if you're a newspaper or something like that, your content is copyrighted, and so you can put it behind as high of a wall as you would like to put it behind. Okay, so that's very, very interesting. It's another thing to think about. Food for thought. Okay, so if we talk about ads in general, you can ask our boys that question, and you can come up with your own answer yourself. It's like, are ads a good thing on the internet? Is it good to have an ad blocker, to make one of those? Because like there's a reason people are putting ads on their website, right? Because they make money that way. So you have to think about, is it ethical to block those ads that they're trying to show to us? All right? So again, you can ask our boys, Kant, the fan of individual rights, probably also privacy, would say, all right, he would ask the question with the word always in it. Should we always be looking at the ads that are shown to us? Because that's like the alternative, right? So if we're given an ad, are we meant to always look at it? Should we always be clicking on every ad that we see on the internet? Should we always buy the products that are advertised to us? Because like if you see these blown up in your face all this time, like obviously there's a purpose. Should we be always doing what the ad says? And definitely the answer is no. That's like using people as a means to an end all over again. It's not okay, right? You wouldn't want to do that always, and so it's not worth it. So ad blockers, I would say, are a good thing as far as Kant is concerned. You'd say, yes, let's have ad blockers. But on the flip side, you can also ask a utilitarian, and they would start to make their pro-con list, right? Start weighing the matter. And so what are the benefits would be the question that a utilitarian would ask about this stuff. So what are the benefits of having an ad blocker, right? what are the disadvantages of having an ad blocker? Well, if you are the consumer and you install an ad blocker, like and you go to some website with the news or something, you end up getting the news and not anything extra. You have more real content on the pages that you're going to if you install an ad blocker. And so that's a big pro, right? You don't have to look at a bunch of flashing images all day long, and you can get what you're looking for quicker, potentially. So that's one pro. You can also think about the cons of blocking ads, because say you go to a small website, right? And they're not trying to blow up your face with ads all over the place. They just put like one at the top or something, and they're trying to make money, right? So if you block ads on a website, the makers of the website who are installing those ads get less money. Less money for the people who put the ads on their website, and maybe that was the only way they could afford to host that website on the internet, and will go away forever if too many people install ad blockers. So maybe that's cause to get rid of your ad blocker. See that? So you could use these ideas to argue both directions and then come up with the stance that is all yours. Okay? Any thoughts, comments about this? Computer science relevant questions and ideas, right? It's not the ad blockers. What else? Let's see. Let's talk about Google Street View. All right? This is still a thing. So you know Google Street View. Hopefully we've all used it before. You just you enter an address, or you can just even click on a Google map, and it will show you a picture of what the road looks like there. So I use this all the time. Like if I go to some new place, I want to know what the outside looks like, so I don't miss the turn or something. So it just so happens that certain countries, like Germany, are not a fan of Google Street View. Like all the rest of Europe, for the most part, is Google Street View. Like they put their little car through those roads and they took pictures. But Germany, notoriously, does not have Google Street View in most places, especially rural areas. Okay? So Google Street View is pretty much everywhere else in the world, except for Germany. So it's a little weird to think about. And you have to ask why. Why wouldn't the Germans want this? Okay? It's a privacy thing. Because the Google Street View car is coming around and it's taking pictures of your house. Right? As an American, I guess our culture is like, yeah, that's cool. I like that. I want that because I want to go and look at somebody else's house. Right? If I'm trying to go there. But Germans are a bit more big on privacy. So culturally, Germans are more mindful of their privacy, and they've made laws that prohibit that kind of just like mass gathering of images. Okay? Especially in the rural areas. That's such a hard word to say. So, yeah. That probably makes you think, right? Are our ideas the right ideas? Who knows? It's an American thing. It doesn't have to be a world thing. Any thoughts, ideas about that? Have you even considered, like, that's an invasion of your privacy? Having your house or your apartment be pictured on Google Street View? Some people do. So, there is a way, actually, to have your house blurred, I think, even in the U.S. on Google Street View. So look into that if you're interested. That's the thing. So yeah, that's privacy. Do we have it? Do we not have it? Should these things exist? Should they not exist? So just a bunch of ideas to get you thinking about it, for eventual essays, of course. Let's next talk about encryption. Right? That's the process of like taking something and jumbling it up so that nobody else can understand it other than the person you're trying to send the information to. That's the process of encoding information. It's making it look very ugly to anybody who tries to peek in on it. Okay? So only the part the concept is like there's a message, right? There's a message and you encrypt that message, and only the people who have the key, right, are able to decrypt it or decode it. Okay? That's the idea. That's what encryption is all about. It should be impossible for anybody listening in on the tapped phone line or something to understand what the message was if you encrypted it. Okay? So today, the main uses of encryption that happen all the time are for security purposes, like you're logging in with your password, make sure that nobody can view your password as it's being sent around the internet, trying to log you in, and then also commerce. So it has to do with the security of commerce websites as well. Like you enter in your credit card number, you try to click, yes, I want to buy this thing on Amazon. encryption makes sure that only Amazon gets your credit card number and your address and stuff like that. Okay, so yeah, encryption ensures that your credit card number, for example, is only getting sent to Amazon, even though, like, most of us have like Xfinity at home or something like that. Those are like the two major internet providers in Fresno. So even though your information, your credit card number, it is traveling through Comcast, right? You have to get it through Comcast's internet pipes to get it all the way to Amazon servers. It's encrypted across all of that. Okay, that's the idea. So, do I want to show that to you right now? Why not? Sure. So, like, you go to even the class website or Canvas, any website that you go to these days, you see that HTTPS? That S stands for secure. And so that means that things are being encrypted as you're sending information across the internet. So, like, you can click, like, connection secure. Why? More information. It's like, it's verified. There's a certificate that says exactly what's going on. It's like, oh, this is encrypted with this kind of algorithm. Blah, 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 blah. And so that's pretty cool. Every piece of information, even with the class server, you're typing in your password. Nobody listening in on the internet pipes can get your password to the class server. Cool. So we'll come back to that in a second. So that's an interesting piece of information. So that's encryption in a nutshell. Let me show you some examples of encryption. Here's a very simple one. It's called the Caesar cipher, invented, I guess, in Caesar's time. It's also called ROT13, which stands for rotate. Rotate the alphabet by 13. Rotate 13. So this is a very, very simple, completely broken encryption. But maybe in Caesar's time it was really cool and nobody could understand it. So the idea of the Caesar cipher, or ROT13, is that you take every character, like if you're trying to encrypt the letter A, you'll shift it 13 in the alphabet, and so you'll get to N. So every time you have A in your text that you're trying to encrypt and send to somebody, you'll write N instead of A. Okay? That's the idea. So if you're trying to type hello to somebody, you'll send, instead of hello, you'll send yib, apparently, because all those become those, like the H, the E, the L, the O. Okay? And when you go past the Z, you wrap around back to A, so O gets to be B. Okay? And the nice thing about the Caesar cipher is it is its own inverse, because there's 26 letters of the alphabet and 13 is halfway. So, like, if you encrypt A, you send it 13 down the alphabet, you make N. And once you have N, you just apply it all over again. And that takes it back to A, which is kind of nice. So that's the Caesar cipher. That's an old way of encrypting information. And so it looked like this, and like nobody but the people in the know knew what it was. But nowadays it's very easy to crack it and understand. Like, oh yeah, it's just the Caesar cipher. Not good enough for the internet, right? Your password is not being encrypted in this way right now. It's being encrypted in a much more advanced way that was invented in the 70s and is still the gold standard to this day. It's called RSA. It's an encryption algorithm. It stands for the three last names of the people who invented it in the 70s. And RSA, it's an algorithm, it's a computerized process that involves, like, the thing you want to send and a key. There's some certain metaphor, right? There's a thing called a key. There's two kinds of keys in RSA. There's one that lets you encrypt your message, your cloud that you want to send to somebody and make it look all jumbled. And then there's a separate key to decrypt somebody else's message that they send to you. Okay? So here's RSA. There's a key to the encryption. It's publicly available. You share your key for encryption to everybody you ever want to talk to. It's out in the open. So anybody can send you a message using this public key. Okay? So if somebody wants to send you a message, you give them your public key, and they'll encrypt it back to you. So here's the setup. Here's you, and here's the sender of a message, a secret message to you. Here's the sender. So they want to send you a message, and so first you're going to tell them your public key, and you can just say that out in the open with anybody allowed to listen. Totally fine. So you give your public key to the sender and anybody else, whoever wants it. And then the sender uses that public key to take the message that they want to send to you. Here's like the little envelope. Here's the message that they want to send to you. They encrypt it using that public key. So they use it. Okay? And then there's a separate key to decrypt it. So this was invented back in the 70s. It's still the gold standard it's that secure if you use big enough numbers. It's a math kind of problem, okay? So there is a secret key that you don't share with anyone. There's a second key called a private key to go along with the public key that's just yours. You don't share with anybody. That lets you decrypt all the messages that were sent to you using your public key. So you have your own little private key over here that is secret and yours. And these, at the end of the day, this is an algorithm on numbers. They're just big numbers. The keys are just big numbers. Just like messages are just big binary numbers, right? So this is your private key. And you use that to decrypt any message that was sent to you and encrypted with your public key, right? So it's kind of like the inverse to the encryption. And RSA works because it's really, really hard to factor numbers. It has to do with prime numbers that are very large, and multiplying numbers together and finding out the factors involved with giant numbers is a computationally very, very hard process. And so it would take like millions of years for modern day RSA to be cracked by a computer. Just have to try that many different numbers. It would never figure it out. Okay, that's pretty cool. That's RSA in a nutshell. Let me give you an example of that because it sounds kind of vague right now. It's just a math problem, okay? So here's the tutorial. Everything's a number, first of all, in RSA. Your message is a number, your private key is a number, your public key is a number, okay? So actually your public key is two numbers, okay? So your public key is, let's see, I'll tell you about modular arithmetic in a second. Modular arithmetic is like the backbone of RSA. It's just the idea of using that modulus operation, taking the remainder after doing some math. Okay, so remember the remainder operation. So, all right, your public key in RSA is two numbers, n and e. So you get some number n and some number e. All right, that's your public key. You give that to anybody who asks for it, and then you save away your private key. That's a different number called d, at least in the algorithm write-up. And all these three numbers that make up your public key and your private key are generated from two gigantic prime numbers. Usually these numbers are so large I couldn't even put them on the slide. Okay, so these are just small sample numbers, but in reality these are much bigger. But yeah, these numbers are generated from two gigantic prime numbers most of the time. And the secret is that D and E, like one's part of the public key, one's part of the private key, they are what are called modular multiplicative inverses, which is such a huge mouthful. All it means is that you have some message you want to send to somebody encrypts it with the public key, like you take it to a power of E essentially, and then they give you that, they send that to you. And then you can decrypt it by taking it to the power of your decryption key. And then you always do the modulus, right? So these are equal to m if you do the modulus by the number, like m, okay? Or sorry, n, I believe, yeah. Mod n is the idea. So you just do the remainder by n on both sides. They will be the same. That's how they become inverses of each other, even though there's nothing but whole numbers involved. So don't worry too much about that. It's just math. Let me give you an example. So with these particular numbers, you can send, or just in general, you can send any message, m, call it m, between 0 and n minus 1. The biggest thing, because you're taking the remainder after dividing by n, so the biggest number you can get after you do that remainder operation is 1 less than the number, right? Because if you divide by 2, for example, take the remainder is at most 1. Same idea. So, okay, you can send any message between 0 and n minus 1, and usually n minus 1 is a large number, but for our example, it's small. So let's say that we want to send the secret message to somebody that is the number 42. Okay, that's our secret message we'd like to send to somebody, and so we'd like to encrypt it so we can send it across the wire. So we ask the person for their public key, we get it back, it's n and e, and we're going to calculate m to the power of e mod n. So mod is just that percent sign, the remainder operation. And that's going to be called C. C stands for ciphertext. That's the encrypted form of what we're trying to send. So we want to send 42 to somebody, all right? So let me pull up my handy-dandy calculator. Let's do the terminal. So we're going to calculate 42, that's our number, to the power of E, which is 17. So 42 to the 17th power is that giant number. And then we're going to take that mod n. We're going to do the remainder by dividing by n. So it's a lot of math. 3233. And so apparently our ciphertext This is the encrypted form of 42. We're going to send that to the person. Hard to crack. It's 2557. So that's the number we're going to send across the internet publicly. Anybody can listen in. They're still not going to know. All right, if these numbers are big enough, at least. And so now, if we're the person who received that message, the 2557, we want to know what was really being said to us. We'll decrypt it by calculating that message to the power of D, also mod n. Okay? So I'm going to take 2557, take it to the power of D, which is 413. So it's that giant number. We compute this giant number. Where is it? It is very large. Wow. So you got to do all that. And then, even for these small numbers, it's huge. Then you do mod n, 3233, and just magically, because of the way the math worked, the very smart scientists back in the 70s, you get the number 42 out on the other end. So that gives you back your original M, and that is RSA encryption, is the backbone of the internet. It's the way that things get transferred. Even the class website, its certificate, it's like, how is all this stuff being passed along? RSA encryption. Cool. So that's pretty nice. Okay, so yeah, that's RSA in a nutshell. Any questions about encryption? It's just a big math problem, at least on the internet. Alright, so yeah. Let's ask this question now, because encryption is a thing. We use it a lot. Is it ethical to use encryption to send your messages, to make something that nobody else can crack, even law enforcement? Okay? So I'd like to have a debate about this. So let's go back to the written nice page. Please press the refresh button so that you don't like redo your own stuff. So I'm going to delete everything that was there. So refresh your written nice page if you still got it open. And I'd like you to get into groups, please. And then you'll elect a group leader. And here's the debate. I want you to ask the question to yourselves. Is it ethical to use encryption to send secret messages to just you and some other person that nobody else can like peek in on? And here I am going to split you into groups again. So if you just, like, you know how to do this now. If you just pick your leader, somebody press submit with a blank post, and then you'll get a group number. And then if you're even, let's say, if your group number is even, you are for using encryption. All right? So I'd like you to come up with at least 2 arguments in support of this stance. Like if you're an even number, you're for encryption. Give me 2 reasons why encryption is a good thing to send messages, even if nobody else gets to listen in. If you're an odd-numbered group, you got to say that you're against encryption. Okay? Give me at least 2 good arguments as to why it might not be a good thing to let people just send whatever messages they want to each other without anybody allowed to listen in on it. Okay? So give that an idea. Think about the boys if you want, but I'll do that with us at the end. But take a few minutes to write up your ideas, and remember to press submit again after you've written up your ideas so that I can see them. Okay? So that's that, and yeah, good luck. I'll give you a few minutes to discuss. So even if you don't think the same stuff, this is your stance I've given you. Alright, take another minute to synthesize your thoughts and get them in there. Alright, 30 more seconds to get something in there, click submit. I'd like to see what you're thinking. Alright, that's my timer. Let's come back and see what we're thinking. What do we got? Nice. Alright, what was it? It was even for, odd against. So yeah, let's see some good ideas. Against first with group 73. Encryption is not a good thing. Underlines law enforcement. That's a big one, yeah. Prosecuting crimes, because like people saying bad things, trying to commit crimes with each other, are going to try to use encryption, obviously. So it'd be nice to be able to break into that somehow. Led to terrorist attacks. Had encryption not been available, terrorists could have been caught prior to their acts. If you were able to sift through all the messages, absolutely, you could definitely find or get people who would have committed crimes. You can get them behind bars before they would do it. Good. Let's look at an even group. Let's go skip to 76, let's say. Oh, I like that you looked into Kant. So what would Kant say? Encryption allows people to hide things they deem important. Kant is for individual rights. And he would probably, then you can conclude maybe that he'd be in favor of that. Enables You can send information without fear of repercussion, promoting the exchange of information for the benefit of society. I like that. Just to be anonymous. If you want to post something that is maybe a little like a new idea that you don't want to put your name behind it, it would be nice to be able to post it anonymously so nobody could see like what was going on. So you want to send it in encrypted form so that nobody can trace it, stuff like that. It's totally important. All right, these last two groups, let's see. I see crime again. That's an important thing. The network is already public, so you shouldn't be assuming that things are private in the first place. I like that. And then one more for encryption, protection of privacy, meant for whoever it's being sent to. Yeah, it's just, if you're pro privacy, you would be pro encryption. Yeah, don't want some random guy to have my bank information. Exactly. But maybe like there should be a level of it. That's like a middle ground. Maybe there should be a back door for law enforcement or something. I don't know. So that's what people have been arguing. But yeah, these are great ideas. I'm glad that you thought about that kind of stuff. That's exactly what I want you to think about. So, okay, together, let's think about what the boys would say. What would Kant say about all this stuff? He'd be like, well, he's for individual rights. He'd probably be like, I can keep whatever I want private. Private info should remain private. And then, let's see, what would Mill say? Utilitarian. He'd be like, pro-con list. Well, it's really good with privacy. If you want any amount of privacy in your life, you probably are for encryption. That might weigh the scales in that direction. But there's also a con, is like, it's harder to protect people from harm, right? Because people can collude over the internet in an encrypted way that may cause harm eventually. And so that could be a con, and that could outweigh things. So yeah, good thoughts. There's plenty more where that came from, but that is a good start. Okay, so I need to give you a new essay, and so to get there, let's go through one last little sequence. I think I need to skip one of these just for the sake of time. But I'm going to talk about 3 ideas that also exist in the textbook, if any of us actually bought the textbook. But here are 3 people or events that took place having to do with privacy. Okay? So let's see, back in 2010, Chelsea Manning, who I think was in the military at the time, it's been a while since I looked at her Wikipedia page, what she did is she gave WikiLeaks, if you remember that, it's a big controversial place that like posts stuff that they didn't own. Chelsea Manning gave WikiLeaks about almost 1 million classified or unclassified but sensitive military documents and diplomatic documents. Okay, so very important stuff that nobody was supposed to look at. Okay. And so, first of all, just taking a step back, this kind of leak that she did, she was a whistleblower, this kind of leak before the internet is absolutely impossible, right? There's no way to give that many documents to somebody, like, easily. You'd have to be making physical copies, yeah? So this is inconceivable. Thanks to the digital age, this came out. And I forget exactly what was leaked about it. I think it had to do with stuff done by American soldiers in Afghanistan that involved civilian deaths that nobody knew about, and so it's kind of like giving rise to like anti-war in Afghanistan kind of stuff. But go back to the Wikipedia page if you're interested in learning more about that. But at the end of the day, even though she brought to light these bad things that nobody knew about, she was still sentenced to 35 years in prison for that leak, and she is out today, though. Her sentence was commuted by President Obama a few years ago when he was still in office. And so this is a big question. She knew what she was doing was against the law, but she thought this information was supposed to go out there. And so she broke the law by leaking these documents that maybe had people's names on them. WikiLeaks is notorious for forgetting to blur things out. Like, it's very hard to do it for 1 million things. And so that might have put them in danger, stuff like that. And so there's a lot of tug and pull there. There's a lot to think about. Should this have been done? Is it okay? Does the value of informing the public outweigh the value of confidentiality? Outweigh the letter of the law? Okay? This is a big, heavy-hitting question that I want you to think about now. All right? So what are the two sides of this coin? It's like, all right, if you have confidential documents and they're like locked away, even if they say bad things, confidentiality protects people, right? Confidentiality. At the end of the day, it does protect people from stuff. If your name is on something and it's confidential, nobody can ever look you up, but now they could if it gets leaked, and WikiLeaks forgets to blur stuff. On the other side of that coin, this is probably the reason that Chelsea Manning went through with this leak. The more info you give to people, the better choices they can make, right? They didn't know about the kind of stuff that was happening until these leaks became released. So more information gets out there for people to look at, maybe for voters, because that was a hot topic of elections, the war in the Middle East. So more info could be given to voters if you allow this kind of stuff to happen. And then also activists who are trying to promote change. This is great firepower for activism. Okay, so it's an idea to think about. Chelsea Manning. I'll have to skip over the Panama Papers. You can read about that on the Wikipedia if you like, but it's another leak having to do with financial documents this time, showing that people were doing some shady stuff. And then the last thing I want to talk about is Edward Snowden. Okay, so hopefully we've heard of him before, but he leaked a lot of classified information back when he was a contractor for the NSA. He leaked a bunch of documents that were classified, so against the law for him to leak them, back in 2013, showing that the NSA was breaking the law. It was spying on U.S. citizens when it should not have had that power. It put backdoors into popular services that everybody was using, like Facebook, for example, that were thought to be encrypted but weren't actually fully encrypted. So he brought that all to light to us. And so the NSA was breaking the law, technically, and they were capturing a lot of information that they should not have been capturing. And so Snowden thought that was a bad thing, and he leaked that information to the public, and that was against the law to do so. Okay? He was indicted for espionage, and I'm pretty sure he had to run away to Russia, where there is no, where we don't have any agreements with Russia to take somebody away if they broke the law. He's currently living there with his wife to avoid prosecution, because if he goes to any country that has any ties with the U.S., he will be arrested on the spot for what he did. Okay? So that is Edward Snowden. Definitely look him up, because he is going to be the topic of your next essay. So let me release that. So another word for him and also Chelsea Manning was whistleblowers. All right? They blew the whistle on something that they considered to be wrong. And so here is your essay idea. Okay, here's what I want you to think about. Here's your prompt. This will be due, let's see, week 6, so 2 weeks from now, maybe 3 weeks from now. February 13th at least. Okay, day before Valentine's Day. Here's your question. Was it right for Snowden to blow the whistle on the NSA, to leak all this stuff, to get all that information out there? So that's your first question. Also, do we even have a right in the first place to privacy on the internet? Because that's what the NSA was looking into. Do we even have a right to privacy on a public utility like the internet? Because PG&E, for example, that takes care of giving us power, they're monitoring how much power we're using all the time, and we let that happen. So why is that okay, and not whatever I do on the internet is allowed for people to look in on? Okay, so that's your prompt, and I'd like you to write just a short essay, 500 words about this. Regardless of which stance you take, I don't care if you have a strong opinion, I don't care if you don't have an opinion, you have to mention both sides of that argument, like the people who are pro-Snowden, the people who are against Snowden, right? And use them to prop you up or bash them down, right? Use them as firepower in one way or another. You can talk about Kantianism or utilitarianism, but you don't have to. And you are also required to cite at least one source in your essay. We still got 3 minutes. One source, please, in your essay. And I'm sorry, but your predecessors have forced me to say this. I need you to cite stuff in a normal way, please. So pick a way to cite stuff, but don't just turn in a works cited page and then don't ever mention the thing you cited in your essay. Don't just say okay, here's a source, and don't ever actually use a parenthetical or some other kind of citation in your essay talking about that source. All right? So if you turn in a works cited page without any actual citations, then I will give you 0. But I'll let you fix it. All right? Let's see. You're also not allowed to cite Wikipedia like every English class. Just go to the articles that Wikipedia cites and cite those. Okay, that's fine. So yeah, I want you to actually cite something in a way that is understandable. All right. So you can pick any format you like, but remember that in order to cite something, you have to quote a source or paraphrase the source You got to put a marker, like some parentheses, being like, this person's last name, this is what I said, they said this, right? And then you got to put a line on the works side of the page, okay? So that is your essay. Remember to cite a source and actually use an in-text citation. 500 essays about that topic. One thing, you must cite at least one thing, okay, that isn't Wikipedia. Any questions about that? So that'll be your next essay about Edward Snowden. Remember to mention both sides. Give me some good arguments, and that's, yeah.
If we happen to have the book, does the book talk about this?
You know, I believe it. I know it talks about Chelsea Manning. I forget if it talks about Snowden, but most likely it does. So you're allowed to cite the book if you'd like.
Okay.
For sure. Good question. All right. If we are good, that is all that I have for us.